I'm Bart. I'm a developer at Microsoft. I'm working currently in the online services division, but my big passion is actually virtual machines, languages, all the kind of nitty-gritty stuff. And so I'll leave it to the imagination to think what I'm working on in online services, if that's my passion. But so the format of this talk is pretty simple. I have a little a la carte menu over here of a number of language features that we can actually talk about. We can talk about many others, but those have some interesting things to them. And we won't be able to talk about all of them, of course. So the idea is for the audience to pick and choose. So, please compose your menu. I can pick some things as well at some point, if, I think there's something interesting to be said there. So, anyone wants to have a first crack at something that looks mysterious or that looks trivial, and you wonder, what's so special about that? Iterator state machines. Let me actually poll the audience a little bit, okay? So I can maybe order the things. Something else? Dynamic dispatch, and maybe a third one. What? Anonymous types. Okay. So dynamic dispatch, anonymous types, and iterators. Let's actually do a little warm-up exercise with anonymous types, because the anonymous types kind of have a number of interesting features to them that you may not have heard about before. So the format of this talk is pretty simple. We're not going to use any fancy tools other than, cmd.exe, csc.exe for command line compiling, Notepad is our beautiful source editor, and ILDASM to take a look at what's going on. So let's just, start with creating anon.cs, okay? And maybe I should have prepared this to be a little bit bigger. And so, we're just going to start, with a static void main, of course. And this is more Java than anything else, so now it's much better. And what we want to write is an anonymous type, okay? So the first thing that you may not know is that you can actually do an anonymous type without any members in it. It's kind of useful. Basically means, it's something that represents nothing. Well, that can be useful. But let's actually stuff some things in there. Let's do b equals 42 and c equals bar, okay? So pretty simple anonymous type over here that contains two properties. Now, one of the features in C# is that anonymous types are immutable, okay? So you can't actually assign to any of those properties in here. In fact, in Visual Basic, there is a little difference there, and then I will explain why it's important. In Visual Basic, you can actually write something like dim a equals new with, and then you can say over here, dot b equals 42, comma, dot c equals bar. But you can also indicate the properties that actually participate in a key relationship. So you can actually tell which ones have to be immutable versus which ones shouldn't be immutable. Okay? So that's an interesting little tidbit, but it will become useful in just a second. So let me actually try to compile this. I hope it looks okay, but we'll confirm. And so here we go. Now, I won't talk about all of the anonymous type features. Oh, this thing doesn't remember. I promise, I set the font sizes just a second ago on this one, so let me just keep this instance open and just do this. So, as you can see, the anonymous type is being generated over here. How many of you have never seen ILDASM before? Okay. There's still time to leave the room. No, just kidding. So ILDASM is just this thing that actually looks at, what's going on behind the scenes. So that's really the metadata format that the CLR knows about. It doesn't know about C#. So this is the intermediate language disassembly. There's also a tool called ILASM, and you can actually pair those two. So you can do round tripping. You can say ILDASM/out equals something. Then you have IL code, and then you can change it and then reassemble it if you like to. So let's just take a look at what's going on here. And the reason it's actually a generic type is something I won't get into. It has to do with visibility. There's a great blog post by Eric Lippert on why anonymous types actually use generics. So let's ignore the generic part. But you can clearly see that, the anonymous type actually has two init-only fields. Init-only fields is the IL lingo for read-only. So it means you can only assign to it from the constructor. As you can see, the constructor, well, that's already a little bit interesting. There is a constructor defined for the anonymous type that actually takes in the two parameters, one for B and one for C. By the way, whenever the C# compiler generates a name, it actually uses this mumble syntax, less than, larger than, some number, underscore, underscore. The numbers actually go up increasingly by release. So by the end of the session, you should actually have seen, I think, A through maybe H or something. So we'll see how far we get in there. Now, what's interesting is that, we have two properties here. Those triangles are actually the properties. They're instance properties. And when you see this bang thing, bang 0, bang 1, it means it refers to the type specified in a generic parameter. So bang 0 means, whatever the type is of the first parameter, which is, this generic thing. So let's ignore that generic thing for now. But as you can see, they're only get-only properties. So in Visual Basic, you can actually say which properties are get-only, which ones are also settable. So that's an interesting thing to see. But what's more interesting is actually the implementation of equals and get hashcode. Equals and get hashcode, and in fact also toString, are actually implemented for anonymous types. And the reason we actually implement those is because anonymous types are typically used for things like doing things like, a join in link. A join in link may say, well, I want to join two tables based on composite keys. So you want to say, like, I want to join the products table with some other table, and then you want to have some equality expressed in terms of an anonymous type. So they need to actually have meaningful equality other than reference equality, of course. So what's going on in the equals method is really, and I don't expect you to be fluent at this point of reading all of this stuff. So let me just show and point out a couple of things. It basically just calls into the equality compare of the left-hand side and right-hand side, or of all the different properties that are defined on this type. And so it basically just gets the default compare. So it does equality compare of t.default. In my case, it actually does that once for the int, for the B, and once for the string for C. And those actually dispatch into the virtual equality method that's defined for those types. So it does what you expect it to do. Now, the important thing here is that it basically just compares all the fields or all the properties in a pairwise fashion. Now, what's also interesting is that it expects, the other type, the other thing that you compare it to be of type exactly the same one as you start with. So they need to match in types as well. So the CLR doesn't really have any structural equality defined between types. So the only thing that C# does here is basically check that types are the same, and then make sure that those two things actually line up. Now, one more thing here is that there's, of course, also a get hashcode implementation. The get hashcode implementation starts with two prime numbers, which are kind of essential to creating good hash codes. And in fact, this will always be the same in this release. For every anonymous type, you will find one thing to be fixed and one thing is actually a variable, if I believe, if I remember correctly. But so if you look at this, like it's again dispatching in the default equality compare, and then it's doing some, mumbling of those things together, right? Doing good hash codes. You can't just add up the two numbers. If you add up the two numbers for a hash code for a point that has two ints, well, a point where the x-coordinate is the same as the y-coordinate of the other one, and the y-coordinate of the first one is equal to the x-coordinate of the second one, those would have the same hash code. So you always need to have some offset. So the C# compiler does something like, add the two things together, do some multiplication over here before adding the two things together. So it basically shifts the two things. And those are actually prime numbers if you would look it up. Now, one more thing is toString. And toString actually uses a string builder over here, as you may expect, to actually provide a friendly string for the anonymous type. Now, this is interesting because just by looking at this, you can already imagine, like, what does it mean for two anonymous types to be the same? A reasonable expectation would be that the two strings look the same. So if you look at toString, it first prints B and then it prints C. So if it has an order defined, it also would mean that an anonymous type with the two properties flipped should not be the same as the original one. And let me actually prove that to you, that anonymous types actually unify to the same underlying type only if and only if the properties are exactly the same in the same order. So let me just show you over here what I mean with that. If I have a second anonymous type, var B, where I use 43 over here and Baz over here, that's nice. And let me also have C over here. Let me actually start by just saving this and compiling this one. I should really recompile ILDASM at some point to have default string font sizes. But if you look over here, like, there's only one anonymous type generated, so you will already believe me that those two anonymous types happen to unify to the same underlying one. So that's kind of important. If you're in a method and you're saying, well, I have a collection called foos, and I want to do dot select on that to project it into an anonymous type, and then you have bars, and you also want to do dot select to project into an anonymous type, you would expect those two things to be the same, because otherwise you can't even do something like enumerable.concat. If one thing would be an IEnumerable of the first anonymous type, and the other thing an IEnumerable of the second anonymous type, well, the compiler would say, I can't find an enumerable overload that allows to do concat between two things with different t's, right? Different generic parameters. So they actually have to line up. However, if I actually just flip one thing around here, even the declaration order of those two, like this, then we will have a different anonymous type. So those two will not unify in any means. So kind of important to know that those two things actually result in two different implementations here that don't participate in mutual equality checks. Like, the C# compiler can't know the universe of all the anonymous types that happen to have an A and a B in it, right? So, like, it's basically truly anonymous in the sense that you can't make any predictions of equality, hash codes, and all of those kind of things beyond the scope where those anonymous types are actually declared. So that's essentially, the story of anonymous types. I don't think there's much more to be said about that. One thing I will actually point out is that types that are generated by the compiler can be recognized using the compiler-generated attributes. We'll find, all the things we look at here today to basically use all of that, the same attribute essentially. In fact, if you do link providers, there's something in addition to this that's interesting to point out. I'll just write it down over here, and I'll try to actually get those little demos out to the audience through some means of sharing. Maybe I'll paste them in the PowerPoint slide or something. But if you look up the new expression class, you will find the mysterious members property on that one, which actually has to do with anonymous types. So if inside link, you're writing something like, well, actually, let's just talk about it for a second. I'm kind of the talking kind today. So like if you write this thing in link, if you write from x in x's, let y equals x times 2. Who has seen the let keyword before? Okay. So let basically just allows you to define, a temporary variable essentially inside your query. It's actually not a variable, it's just a binding, a let binding. In a sense, you can't reassign it. But so if you do this kind of thing over here, like let's say select x plus y, what's really going on behind the scenes is that the compiler translates this into x's dot select of x goes to new, and then it will actually put in there x comma y equals x times 2. So it's basically creating anonymous types for all of the let keywords. It's basically doing intermediate projections that sort of carry around all of the state that's in scope. So I may actually have another one here, like saying let z equals, y plus 1 or something. I'm just making up something here. It doesn't really matter, like, as long as it compiles. But so what's going on here is the compiler generates all of those intermediate stages here. For link to objects, that can actually be a performance penalty if you use a lot of lets, because it will actually generate those anonymous types that are actually Gen 0 collections typically, which isn't that bad, but it's useful to know. But what's going on over here now? So in the first let, I basically, at that point, I have both x and y available, right? Like, those are the things you expect to be able to use inside your query expression. However, then here I have let z equals, let's say, y plus x. Now I need to be able to refer to those two things. So it's basically creating those anonymous types that carry along all of those variables that are in scope, or all those bindings that are in scope. So how would it translate this line? Well, let becomes a select, and now, of course, the input to the select is whatever the output was of the previous part of the query. So how can it now actually compute something like y plus x? Well, the answer is, of course, like it can do z equals t dot x plus t dot y, because like t is now something that represents an instance of this type. And of course, I also want to keep tracking along t, because at some point in the next select, a real select that the user wrote, I want to do x plus y. Well, let's actually do x plus z over here. So again, I have to refer to the last stage of my query, and now here it can actually project out x. How can I get to x? Well, I can get to x by starting from the current value, and then I can dot into t, and then I can dot into x. So this actually becomes t dot x plus, and then over here t dot z. So that's really how this little link query translates. And now this feature of t, those t's are actually called transparent identifiers, if you look in the language specification. Now, what's interesting about it is that if you're building a query provider, you sort of want to track those things through. You want to sort of see the final selection, and you see, well, the user wants to do t dot x. What does that really mean? So you actually see a property lookup, and now you need to know where that thing comes from. And that's actually what this new expression members property is for. It basically says if you have an anonymous type, and this was the first parameter passed to the constructor, this parameter will come out on the other side as this property. So it actually does a correlation between constructor parameters and the properties that it actually assigns. So that's kind of an interesting thing. If you ever build link providers, it's very useful to know about new expression.members, because it allows you to build an environment lookup table, essentially. So that's a little, a side story here, and let's make sure this still compiles in case, I can share it out. So the best way to make things compile is just comment them out. Okay, good. So let's actually jump back to the slides. So we covered, in fact, by just doing this, I actually secretly covered query expressions let classes, which I sort of wanted to talk about anyway. And we talked about anonymous types. So then we had iterators. Let's actually do iterators first, because, well, iterators are related to link, right? So what's interesting about iterators? So first of all, who doesn't know what iterators are? Nobody wants to admit? Okay, good. Everyone knows what iterators are, apparently. So let's just write a very simple iterator over here. Shouldn't be called anon.cs. Let me actually call it it.cs. It's a very descriptive name. So let's just do class program here. And so what iterators allow you to do is just write, something like, well, let's first do static void main, of course. In fact, notepad coding, then you just put the 4 spaces on your clipboard, and you can always do indentation kind of automatically. And so what I want to write here is static IEnumerable of int. And let's just do something very simple, using system and using system.collections.generic. Okay. And so now I can write static enumerable, and let me actually call this thing, get values, right? And we'll actually keep it super simple, because otherwise what we will be looking at will actually start exploding. We don't want it to explode. I could go all fancy here, build something really crafty, but then, the disassembly will actually start looking really weird. So let's actually keep it very simple. Let's do yield return 0, and let's do over here yield return 1. That's enough to sort of get us started, okay? So what this allows you to do is basically you go to get values, and this thing doesn't start executing, right? It's only whenever you do an iteration in the for each loop that consumes it, it moves, the virtual instruction pointer of the iterator one step forward. So the first time you call move next, the first iteration, it will run all the way to yield return 0. If there are any side effects behind that, those will be delayed until the next time you call move next, right? That's the whole point of iterators. So in fact, like if over here you actually send the missile to Mars, and you break out of your loop, after consuming the first element, there are no missiles being sent to Mars, right? That's basically the idea. So that also means you can have an infinite loop here. Like it's only as infinite as the consumer decides. If the consumer decides to break out quickly, well, then it doesn't run all that long. So let's take a look at what's going on if I compile this thing. Okay. So as I promised you, you will see another letter of the alphabet at some point. So in this particular case, we'll start seeing D underscore. D is for iterators. So what has this thing actually compiled into? So get values, which is my method that I actually started with, doesn't do much, right? It basically just says, somebody asks for a get values iterator, which is an implementation of IEnumerable, please new up one of those guys, right? That's the first thing that this thing does. One thing that's interesting here is the first instruction, though. The first instruction says I want to load a constant value of integer of 4 bytes. The .s part I can talk about in just a second, but it loads something with value -2. So this is kind of a virtual instruction pointer for the iterator. Like, it needs to remember, like, whenever somebody does move next, like, oh, what's the next piece of code I have to execute? Now, of course, if you look at the code that I have in my C# here, it's kind of straightforward, right? Just run till the next yield return. But it can be much more complex. You can have like loops, you can have for each statements, you can have using blocks. Like, it really needs to know where to jump next to execute the next portion, right? It may say yield return 0, and then it may do something like, while true, do something else, maybe with a break statement in there. Like, every time you call move next, it needs to pick up where it left off the last time. So that's kind of important to keep in mind. So this -2 is actually nothing but just getting the initial value of the state machine, and it's actually passing it in a constructor over here. Now, one thing actually before I continue here, if you're an IL freak and you actually look at this thing, you will actually say, well, what's this about? Why do they store something in a local variable, then to load it again, and then store it in a different local variable, and then to branch to the next label? And then, like this is all redundant stuff, right? The thing is, this is just how the compiler emits basic blocks, and actually also does it in such a way that actually the debugger experience is kind of good. For example, if you have, regular statements, for every curly brace in your statement, you'll actually find an op statement in the corresponding IL code if you're in debug mode. Why? Because if you don't have a statement or if you don't have an instruction, you can't set a breakpoint on there because the CLR wants to have an instruction to associate a breakpoint with. So every curly brace that you have in C# for regular statements will actually result in an op statement as well. For example, here static void main contains an op, which is the opening curly brace, and then the ret is the closing curly brace, so we can set breakpoints on that. However, if you actually, this is a little tangent, if you do /o+, which is the optimize flag that you can actually set in Visual Studio, if you do this, you will actually see that the NOP statements are gone, the optimizer has run, and it has actually pruned out all of those redundant things. In this case, actually, it's still doing a store lock and load lock for a reason I want to take a look at some point. Okay, that's kind of interesting. I think I know why they do that. Okay, but whatever. Let's take a look at this thing. I can actually talk to you about that in the bar. My bus only leaves at 7:30. So what's going on over here? What's going on over here? So this is actually the implementation of the iterator. That's the thing that when you're doing a for each over the the iterator method, that's the thing that actually executes the code behind the scenes. Now, as we saw just a second ago, get values initiated that state machine in a state called -2. And that will actually get stored in a state field, okay? So what's the first thing that happens if you do a for each? Well, the first thing that happens when you do a for each is you do get enumerator, right? That's the thing that actually is the cursor over the enumeration. So let's just start with get enumerator over here. So, well, get enumerator isn't too exciting. It simply, calls some helper method over here to get the enumerator. Okay, that's fair enough. Not that much to be said about that one. It basically dispatches into the generic equivalent over here. So the generic one looks more interesting. Now, the first thing it does here, and this is code that has actually changed in .NET 4.5, slight little bit, is it will check the thread that you're currently on. So that if you do get enumerator on the same iterator state machine, from different threads you get different enumerations. So you don't want those things to start messing up, and one is actually trying to update the state while the other one is trying to do it. So they basically split it off at that point in time. Now, the first line here, and this is just a very, very short tidbit, in .NET 4 and below, it actually used to do system.threading.thread.current, thread.manage_thread_id. It actually is now doing system environment current manage thread ID. The reason for that is that in WinRT, you don't have the thread class anymore, so you can't dot into thread.currentThread. And we still need to have a unique ID for the current thread, so they moved that to the environment class. So if you ever want to print the current thread ID, you can now use system.environment to get to that as well, just like you can get to the current process ID, I believe. So that's what's happening here. They're basically doing some comparison thingies over here. Statements that start with B mean branching. So this means branch when not equal for an unsigned comparison. And S means it's a short jump. Short jumps are less than 128 bytes. This allows, the JIT compiler to do some more magic. But essentially, this thing is just checking, are you still in state -2? If you're still in state -2, I will now kick you off. You did get enumerator. Let's actually start executing the code that the user wrote. So that's already the first thing to keep in mind. And this is very important. If you're in here, right, if you have an iterator, where's my iterator? Here. Oh, that's not my iterator. Did I close my notepad somehow? Okay, whatever. So here it is. Say that this thing takes an int x over here, and you want to say if x is less than 0, throw new argument out of range exception or something like that, right? This is most certainly not going to do what you expect it to do, because this exception is not going to be thrown until you start doing the for each over the thing, right? Because like all of the code that's sitting behind this is sitting behind the get enumerator, it's even sitting behind the first move next call. So like all of the effects of the method are being delayed. So nothing happens until people start enumerating, and that's not the time you want to get those exceptions out. So if you actually look at link to objects, which is implemented using a lot of iterators, all of the argument checking is in helper methods around the iterator methods. So what's really going on there is they basically implement this thing in 2 stages, and this is a very useful trick if you ever implement iterators with argument checking. You basically want to have a pattern that's a little bit clunky in some sense, but you want to have like a private method sitting next to a public method. In the public method, which is not an iterator, it's a regular method that doesn't contain yield return. You do all your argument checking, and then here you return get value simple, of x. Okay, so this code runs synchronously immediately when you actually call the method, and then it returns an iterator that has all the side effects delayed. So everything that happens before the first yield return doesn't happen until the user says move next, which is not the time to throw exceptions. Now, one more thing here is that for Visual Basic, in Visual Basic 11, they just added iterator support, and they've gone a little bit further than C#. They have the notion of anonymous iterators. So you can actually return a little block of code by using iterator, begin iterator, and end iterator that contains the code right there. So you don't have to declare a separate method for that. But so this is kind of the typical style that you use. And in fact, I didn't want to use X anyway, but what else can I say about this? So the state machine is, of course, all about move next, right? You do an iteration over it. You say like for each var x in get values. Like every time, the for each does a move next, it needs to move till the next yield return statement. That's the basic ID. And so that's really all that move next does over here. Move next has a switch statement in it, which you can see over here. It basically switches on the state. And it actually will say, if I'm in a certain state, if I'm in state M1, which is -1, I will actually do some stuff here, and I will update the current value. Now, let me actually change something in the code, because there's a lot of zeros and ones over here. So let me actually just change one thing. Let me return 17 over here, and let me return 23. So we don't have zeros and ones and all of those kind of confusing values in there. So you will actually see where the 17 and the 23 actually come in. In fact, let me do one more thing here. Let me do 17 times, console.readline .length or something. This means that, when you call move next, the first time you call move next, it will actually do a console.readline to ask the user for input. Very unintuitive, but, it's just an expression being evaluated. It will get the length and multiply it by 17, and that's the value that comes back into the for each loop. So that's the thing that actually the consumer will see. So if we do this, just for fun and giggles, and I take a look over here, okay, I messed up quite a few things here. Get values impl, that would be much better. So let's do CSC again, I'll DASM it, and then here we see get values impl. Whenever the compiler generates a helper method or a helper type that's related to a certain method, it tends to put the name of that thing in between the less than and the larger than, simply to correlate it back. But so what's moveNext going to do? moveNext is going to say, well, if it's the first time you call moveNext, I need to do all of this mumbo-jumbo over here to load constant 17, to call console readline over here, then to call the virtual getLength property. I'll talk a little bit about the virtual thing, and then do a multiplication, and then store the result of the multiplication in a field, which will be the thing that corresponds to calling current. So a for each loop is nothing but while e.moveNext, do something with current, right? So it has to stick that value in a current property. That's really what this thing is doing. And then the next time around, it's going to return over here. What is it returning? Remember, this is moveNext. moveNext returns a Boolean saying, is there anything to follow? Is this the last value or not? Or, can you continue the enumeration? So it returns a constant value 1, which is the Boolean true. So it actually says moveNext, yes, it worked. We got 17 times whatever console readline returned .length. And now that's available in current, so the consumer can pull it out. So that's really what's going on in this whole block of code over here. Starting from 1b, this is actually the first state being evaluated. Now then you see the next state, which is the state parameter here gets updated somewhere. It actually updates the state over here to state 1 on this line. So the next time this thing enumerates, it actually jumps to label 3e. And what does it do on 3e? Well, there it starts doing the code that will get 23 out to the consumer, because the next yield return says yield return 23. And so again, it runs all the way over there, saying with the last return statement, hey, moveNext worked. You can now fetch a value out of it, and the value happens to be 23, which is stored in that field. And then finally, the last time that you call moveNext, it actually executes this state. And this state actually returns at the very end. It returns a constant 0, which is the Boolean false value, and it returns that to the user. So moveNext actually says there is nothing anymore. And it also puts the state over here in state -1. So all the next times that you actually call this, this is evaluated all the way on the top, you will actually jump back to that thing. So when you call moveNext again, moveNext again, moveNext again, it shouldn't change its mind, right? The enumeration is over. So that's actually all of that state mumbo-jumbo that's going on over here. So let me actually show one more thing in that regard over here. Let me just show you how, like, for example, link to objects implements the where method, just to give you the appreciation for it really being very complex as well. So I can do static IEnumerable of t, where of t, generic method, that takes in, well, I won't declare it as an extension method, otherwise I have to change my class to be static. But so I'll just have a function of t to Boolean over here, which is the filter. So link to objects is basically implemented pretty much like this. In fact, where is implemented slightly differently. It actually glues itself together with other wheres, so it does a little bit of more mumbo-jumbo. But essentially, it does a for each var x in source. For each value, it will evaluate the filter, right? If filter x, and then 1, 2, 3, 4, it will yield return x over here. So that's essentially what it does. But now, if you start looking at this, where's that yield return? That yield return is in the middle of a while loop, right? Which is the corresponding loop generated for each. And how is a for each generated? It uses a using statement. So like there's a lot of stuff going on here, right? It's actually using for the enumerator and so forth. Let me actually expand it completely. It's like var e equals source.get enumerator. This is what the for each sort of looks like. There are some exceptions to the rule which have to do with non-generic collections, but you can do while e.moveNext over here, and then, it basically inside this thing, I should insert some curly braces just for good measures. Inside here, it basically does, something like var x equals e dot current, right? And now in here it returns. So there's a lot of complexity here in the sense that, well, clearly that using statement, it shouldn't dispose the enumerator unless it's the last time you iterate through the loop. Like so now it has to keep book tracking, all of that state as well. And so if you look at the code generated for this, it's a little bit more complex as you may expect, but the idea is still pretty much the same. You look at the code, you draw lines wherever you see a yield return, and then you divide the code into basic blocks. And every block sort of corresponds to an individual state in the compiler, in the compiled code. So let me go back here and just do one more compilation here to show, I won't go into all of the details, of course, of the where iterator over here. The fact that it looks white over here is simply because it's a generic type. Generic types have to be filled up with a concrete parameter, so it's an empty box, while the other thing is a full box. Like there's not that much imagination behind this kind of thing. But you see that there's some more stuff that was actually generated over here. There's this mysterious thing for the generic parameters, and then there is a special method that actually executes the finally body, the thing that's in my using statements. Using statements are really nothing but try finallys in disguise. So, move next has to be super careful, saying, if this is the last time the user iterates, I need to dispose of my source, which is the thing that's happening here. But also, if the user stops enumerating and does a break, also things need to be disposed, right? So if the user does a for each over the while, or over the where, and in the middle it actually says, like, I want to break from this loop, well, if this source happens to be like a database connection or something, you want that to stop if the consumer also stops, consuming the data from the where operator. So there's a little bit of voodoo going on here with those finallys, but all the finally actually will do over here is it will actually dispose the enumerator of the source. The source happens to be encoded using some mumbo-jumbo name here. But so that's essentially the ID. And this ID is exactly the same ID as the ID used for await. The await keyword in C# 5.0 uses pretty much the same technique. Okay? Whenever you have an await statement, well, it's actually not a statement, it's an await expression in your code. The code is basically split up, everything that happens before the await and everything that happens after the await. The only thing is that the state machine is not moved forward by the user saying, please give me the next element, or please give me the next element. The state machine is moved forward by asynchronous completion of callbacks. So for example, if you await a web client, it's essentially the network socket that says, oh, the package is ready, here's the HTML file that you wanted to download, please kick that state machine in the back and move it to the next state. So it's not like a user doing move next, it's basically the environment saying, I'm ready with something, please, at your earliest convenience, continue executing the code to the next wait. And there you have to, well, wait again, right? Not synchronously, but essentially back out, save all your state, and then be prepared for the environment to say, you know what, this await is done as well. So now you can move on to the next stage. So that's basically the idea of all those state machines. So the async state machine I won't get into. Once you sort of get the grips of this one, the other one is kind of fairly trivial as well. So we want to talk a little bit about dynamic. This is actually another demo. So dynamic is this wonderful feature. I actually quite like it. It was introduced in C# 4.0. I don't know how many of you have actually used the dynamic keyword. Okay, quite a bit. Dynamic has this interesting, pretty complex implementation behind it, which actually uses the DLR. Okay, and so let me actually sketch out what's really happening behind the scenes. So let's come up with some example here. So let's just do a dynamic call site and take a look at what's really going on. So I can have, of course, static void main. I should really have copied that template somewhere, but it's not that bad. But so let's actually do an add call over here, static void add. Well, actually, let's do static dynamic add, which takes in a dynamic A and a dynamic B. You can do static dynamic, like it's a static method that happens to return a dynamic. So, and those two things don't cancel out somehow. It's not physics. But so what I will do in here is something very simple. I will simply do return A plus B. Like, why in the first place did you create an add method to do that, right? This is all like just boiling it down to the essence. And the key takeaway of the talk is like there are no secrets, right? You can always compile a little piece of C# just at the command line. Don't get too much tooling involved. And just take a look in ILDESM what's really going on. So ILDESM should be your next best friend, essentially. So what can I do here? Well, I can do something like console write line of add 1,2. Let's do this, for example, and then let's do console write line of A, B over here. And let's do console write line of datetime dot now, time span from days 30 days from now, okay? Those are all things that you can dynamically add together. Because everything is dynamically typed in the add method, there is something that can add 1 and 2 together, obviously. There's something that can concatenate two strings, which is the plus operator for strings. And there is something that knows how to do datetime plus a time span, which returns a datetime. So all of this stuff should actually work, provided I put in a using statement, or using directive better, for the system namespace. So let's go here and actually first see whether this thing works, and then explain what's really going on over here. So here we go. And let's see whether it actually runs at runtime. Okay, that's good. It returns 3AB and then some time, which apparently is 30 days from now. That seems reasonable. So, well, first of all, there is something very interesting happening about even static void main. Static void main is using console write line of add 1,2 and add A, B and so forth. Well, the thing that add returns is dynamic. So dynamic is super contagious. What that means is, when you do add 1,2, it returns something dynamic, and that thing may be an int, maybe a string, maybe something that we can only find out about until runtime, right? And at that very point in time, it needs to pick which overload of console write line to use. And I believe there are like tens of overloads to console write line, which contain params arrays and all of those kind of things. So something needs to resolve where the result of add needs to go. And so, in fact, you have no less over here than 6 dynamic call sites. You have a dynamic call site for each individual add, but also individual call sites for each individual console.write line. So we'll take a look at that in just a second. Now, what's more interesting is the add method, because that's the one that only has one dynamic operation in it, namely doing an addition between 2 dynamic values. So how does that one really work, and why do we have all of that dynamic machinery? Well, the answer is that this thing is self-optimizing using what's known as a polymorphic inline call site cache. Okay, it's a long word, but essentially what's going on here is when you call this thing using 1,2, there's a lot of machinery that needs to happen. In fact, it needs to invoke part of the C# compiler at runtime to say, well, hey Jude, I found like somebody passed in an A and a B, and the runtime type using get type is both int32. Do you know how to add 2 int32s together? And now C# comes along and says like, well, let me check what all my overload resolution rules are, and operator overloading and the whole mumbo jumbo. And it basically checks all of that stuff, and it says, okay, DLR, I know how to do this. I know how to add 2 int32s together, and the answer is you load both of the values, you unbox them into int32 values, you do an add instruction, and then you return the result. So that's kind of the dialogue that's going on behind the scenes between the dynamic language runtime saying, I need some help here. I don't know how to add 2 things together. C#, do you know how to do that? And then they say, oh yes, we know how to do that. Here's the code. Now, once you do that one time, the next time you don't have to invoke the C# compiler anymore. It basically becomes something like the first time you call the add method at runtime, DIL sort of gets rewritten as if A is int and B is int, then, and this is the code that the C# compiler gave the DLR the first time this combination of parameters happened, it will actually say, well, in that case, I do know how to do this. I will basically cast A to an int, I will do casting B to an int, and I will do just the add instruction between those two things. So that's really what's going on here. So that means the first time you call a dynamic method, it's learning, which is kind of a slow process. Like, it needs to be taught on how to do things. But once you do that, it knows, and it's just like, as efficient as the code that you just see over there, which in this particular case, because, dynamic A and B are actually passed in as parameters, happen to be boxed, so there will still be some unboxing cost, but the addition doesn't involve asking the C# compiler, hey, how do you do this? Like, it will literally be an add instruction at the IL level and ultimately at the CPU level as well. So, of course, then the next time you call this method, it says like, oh, I see A and B, which are both strings. I don't have that case yet. Like, I don't have something that holds for this particular case. So I have to ask for assistance once more, right? And the guy to ask in this particular case is actually, again, the C# compiler at runtime in Microsoft.C#.dll. And it will do something similar. It will say, well, to add two strings together, I will give you some code to do that. If A is a string and B is a string, I will actually return string.concat of string of A, comma, string of B. In fact, the C# compiler, when you simply write A plus B in code, there is no operator overload for that. Basically, the compiler says, well, to do A plus B, that means doing string.concat. And like if it's A plus B plus C plus D, all the way to 4, it becomes a string concat with 4 parameters. After that, it starts basically building a binary tree kind of thing to stitch those string fragments together. There is no plus operator on system.string, if you will. It's just an illusion that C# provides. So that's what's going on here. It basically returns, hey, dear DLR, the next time you see this, don't ask me again. This is the way to do it. And so what's actually dangling at the bottom of this whole multi-way if, else if, else if, else if kind of thing? The last thing is, well, oh my, need to ask the C# compiler for help. So that's essentially what's going on here. Like, it starts learning, and then at the very end, well, this is a case I don't know about. I better get some consultancy here, get some answer on how to do that, and then I will stitch it in. So that's basically the idea. So let's actually ignore this and actually take a look at the compiled code to get an idea of how this sort of works at runtime. So let me actually compile din.cs and go to din.exe. So over here, you see something beautiful called site containers. In fact, it's so beautiful that this time it warrants going into the menu once more to boost the font sizes a little bit. So, oops, should really file a request to store that information in the registry. Where else would you put it, right? But so if you take a look here, first of all, dynamic, doesn't really exist. It's purely a compile time piece of magic, right? So if you look at the add method, which in C# I wrote as something that returns a dynamic and takes in two dynamics, in reality, it's something that takes in two objects and returns an object. There is no mythical system.dynamic type in the CLR. However, on top of that, all of the parameters actually do have a dynamic attribute on it. So compilers can see, well, this is really a system.object, but I need to resolve things against it by using dynamic typing. So it actually puts a dynamic attribute on those parameters. So that's what's going on here. Now, what's inside this thing is kind of interesting. Let me think about what are we looking at? We're looking at the add method. Okay. So what's in the add method is, well, it looks like a whole bunch of stuff, right? And you're right to say there's a whole bunch of stuff here. But the essence of it is that the C# compiler will say, at runtime, somebody needs to call me back. And I need to know the context in which the user wrote this piece of code. I need to understand when somebody at runtimes asks me, how do you do the addition? What the user really meant. So we need to be able to tie that stuff back. And so that's what a call site binder does. A call site binder says, I'm going to describe the dynamic operation by just using some runtime objects from the Microsoft.C#.runtime binder. By the way, you can actually dot into that one, but it's editor browsable set to false. So actually, you will not get IntelliSense until you reach this dot over here. Let me actually show you what I mean with that. So this thing actually does have Microsoft.C#. This is just from a previous talk over here. It doesn't really matter. But you can go into Microsoft.C# and runtime binder. Whoops, runtime binder. And it looks, as empty as, the Belgian treasury or something. There's not much in there. But in reality, there's a lot of stuff there. In fact, one of the things that's in there is a C# argument info, for example. There's also the call site in there. Let me actually try to find something that's really in there. The thing is, you almost never have to look what's sitting in there. Let's just do a C#, C# argument info. And poof, all of a sudden the color changes. So we simply have been hiding all of those things from you. If you do have 12 on that, the way you can actually hide those things, for those who don't know, is you can put an attribute on a class saying editor browsable state never or advanced. Advanced is actually something that goes by a checkbox in the options dialog. So if that checkbox is on, which nobody has on, then it wouldn't show up. And you also have never over here. So that's a way of actually hiding things that need to be public for runtime purposes, but you may not want to expose for public consumption. And there's actually a very good reason for that, because those are darn hard to actually use yourself. So the compiler actually emits the code for you. Now, what's the main thing? The main thing here is that it actually uses Microsoft.C#.runtime to create a binary operation. It's basically saying, the user wrote a plus between those two things. I'm going to represent that as a piece of data, a runtime data structure, that when the DLR asks me about it, I still know what was in the original C# code file, kind of. I need to know exactly what the user meant, because, during the initial compile time of my CS file, I can't make the decision. That's the whole thing about dynamic. I have to defer the decision until runtime. So I need to remember just enough information so that at runtime, I can still reconstruct what the user wanted. And so that's really what's going on here. It's basically doing binary operation, and now it's going to say what the expression type is that actually needs to be executed. So it has a whole bunch of flags, and let's not actually go into the flags. But one flag is actually kind of interesting. That's the checked context. So that's actually when the user writes the C# code using the checked keyword, there will be an additional flag that the compiler remembers saying, well, if somebody asks me on how to resolve the plus operation at runtime, and it happens to be in something that was compiled using the checked flag, I need to emit code that actually does a check for overflow. So that's one of the parameters that's passed in over there. Now here's the interesting thing. The way that the C# compiler describes the thing that the user wants to do is using link expression trees in system.link.expressions. And that's really the beauty. The way that the DLR and the C# compiler talk to each other at runtime is like the DLR says, hey, dude, I want to have an expression tree here, a system.link.expressions expression tree that contains all of the stuff that I have to do in order to resolve this operation. And so C# will come back and say, that's easy, it's an expression.add, of, the left thing being cast and the right thing being cast and so forth. But that's the dialogue that's going on. And the reason the dialogue is using link expression trees is because they actually have this super powerful capability of being compiled at runtime super efficiently. But so this is really how the compiler represents the call site. Now let's actually go a little bit further here and have just an idea of what's going on. The one more thing that the compiler does is, besides describing the operation using some data structure called binary operation, it actually creates a call site. Okay, so what's this call site about? Well, the call site is actually stored over here in an object, which is just a nested class. Okay, and so here you can actually see the call site containers. We've already made it to O and P in the alphabet of compiler-generated names, but the second call site you see here is the call site for the main method. As I said before, you really have like 3 console write line calls that need to be resolved at runtime there. So those are those 3 guys over here. What's this one about? Well, this is really our addition. So what the call site container does is it basically is this container that contains all of the state for doing all of those type checks. So this is the thing that sort of, it's the self-learning entity that, like, you know, when you hit it with new parameters, like 1 and 2, it starts learning on how to do dispatch for all the other int32 values it may encounter in the future. So this is really where all of that stuff is sort of happening. Now inside, it contains a so-called call site, which is really the back-end storage for that information. But so every single thing that's dynamic in your code will correspond to a call site container with a call site inside of it. Okay? So now one more thing that I want to point out here is how does the add method, when it executes, updates that call site? That's kind of mysterious, right? I sort of did it here in just C#, but that's obviously not the way things work, right? It's happening at runtime using expression trees. But as I said, like, you know, everything that's in the add method is really stored in a call site. And that thing sort of gets updated every time it learns about a new case. Oh, I've learned about how to add 2 ints together. I'm so happy I could cry. Let's actually insert an if statement and then call the code that the C# compiler gave me. So it's basically doing this kind of, you know, self-learning kind of dance. But how does it do the update to begin with? Well, the way it does the update is basically when it invokes, you know, the target of that call site, it basically passes the call site in as a parameter as well. So the DLR can actually rewrite it and start mocking with it to add another else case to the expression tree and recompile the else case. And in fact, you know, you can actually see the generated code. If we're a little bit lucky, we could actually take a look at that code. Now, this is a part that actually may fail epically. So stay tuned. So let's take a look. Let's actually copy all of that stuff into Visual Studio. And, you know, just overwrite, you know, the last session over here. And, you know, we don't need any of that stuff. So let me see whether we can actually do something fun over here. So what I want to do is, if you were in my last session, you saw that I flipped on this flag called enable remote debugging, not remote, native code debugging. This will allow me to actually load a debugger extension called SOS. And SOS is this debugger extension that allows you to take a look at runtime data structures. It's really like geeky. But so just having this thing on will allow me to inspect the call site of the add method as I move this thing forward. Okay? So let's actually set a breakpoint over here. Okay, I'll set a breakpoint over there. Let me actually just step to the add 1,2 case just by doing F10. Okay, so that's good. So now the call site should know about how to dispatch 2 int variables. Right? If it sees 2 ints in the future, it should do it super efficiently. Like, it should no more bother, you know, asking the C# compiler for help. So what can I do? I can actually go in here in this beautiful immediate window. Let's actually clear it. And let me actually load the SOS debugger extension. Okay? See Windows, Microsoft.NET, Framework, v4.0.30319. That means it was compiled on the 19th of March. And let's actually load sos.dll. SOS stands for Son of Strike. Strike was the original debugger extension that the CLR team used. They created a derivative of that, so it was called Son of Strike. And by the way, and people who were in my last talk just have already heard this, you know, the original code name of the CLR was called Lightning, Lightning Strike, Fusion, like, you know, a lot of things, you know, in the CLR today refer to that. So the Lightning Bolt in ILDASM is one of those things that's a late remainder of the original code name of the CLR. So now that I have this, what can I do here? Well, I can do something like dump all the objects on the heap. Let's take a look at all of the objects. Whoops, I just lost my mic here. Let me try to rewire this. But so I'm just gonna try to get, you know, all of the objects on the heap to see where that call site is sitting. So let's just do dump heap over here. Well, this was not a good idea to actually do it that way. Okay, well, you know, it did it anyway. Well, there's some interesting stuff here. I didn't know there is something at runtime that's using zip. Okay, that's interesting. We'll look at that at some point. So this is the basic idea, right? You know, you go into that kind of thing and you see like, what's that used for? And then you will actually start looking into that, and you learn something else. So you learn something new every single day if you do dynamic and all of those things. So what I want to look at, well, actually, let's just point out a couple of things here. Clearly, the C# compiler has been around. Like you see certain things on the heap here, like expression binary operation, expression list, expression call, expression member group. Like those are actually the node types inside the C# compiler that's sitting in system.C# or Microsoft.C#. So there's a lot of interesting stuff happening over here. Now, what I'm actually looking for is a dynamic method. And in fact, there's a dynamic IL generator, so it can't be too far away from here. But let's actually try to ask for it. Let's see. Can we do this? Dynamic method. Ah, there we go. So the dynamic method is actually, the call site will actually have a dynamic method. What's a dynamic method? It's essentially a piece of IL code that's been built at runtime. That's super efficient because the JIT compiler can look at it and still make machine code out of it. So that's really good. So dynamic methods are actually what's sitting behind link expression trees. If you do .compile on them, they generate a dynamic method from system.reflection.emit. So what I can do with this dynamic method here is I can actually see that there are two dynamic methods. That's kind of interesting. Two instances. And the method table, which is the identifier of the type towards the CLR. CLR only talks in terms of numbers, not in terms of strings. The CLR has two of those guys. That's the things that end with 3C. So those two are actually dynamic methods. Okay, that's useful to know. So what I can do now with dynamic methods is I can actually dump their IL code. I can say dumpil for dump IL. Let me start with the lowest one first. The heap actually grows in consecutive numbers. So I can do dump IL over here. And this is actually the initial call site of the add method before I called add with 1,2. The original call site said something like, well, I want to get the type of both my left and the right-hand side, and then I want to do some decisions based on that. But there is nothing in here yet. Like it's super empty. It's a little bit of, setting the scene, making the table and do some stuff with it. So there's not that much happening here yet. However, you will start to see some very interesting code if I dump the second method table. The second method table is not method table. The second dynamic method is this one. So let me do dump IL of that guy. There we go. What's this dump IL actually contain? Oh, actually, it's the call site for console write line. Okay, my bad. Is this one? Yeah, this is actually the call site for something else. Let me just double check this. Yeah, this is the console write line. Okay, well, actually, it's still interesting. This is actually a call site that has learned that if the operation in main returns an int32, the next time you see an int32 coming back and you do console write line on it, you have to call console write line with the int32 parameter, not the one that takes in the object or something. That's the C# compiler that told us that this is the best way, the best one to use. So let me just step a little further and we'll see more dynamic methods being generated, F10 and F10. So now I have I've called this thing multiple times. I should see many more dynamic methods. In fact, there will be so many that, there will be 6. That's kind of expected. So let's take a look at some of the last dynamic methods here. So let's take a look at one of the 3C guys again, somewhere late in the heap. Dump IL for this one. What's this one doing? This is doing console write line of system.object. There's a console write line overload for system.object. When would this one be useful? Well, the answer is, of course, the last time we called console write line in our main method. What's going on here? Well, we're adding 2 date times. Well, the best overload for date-time printing is likely the overload using system.object. So that's what's going on over there. That's that call site that has learned about how to do console write line efficiently. There should be something more interesting in this list, though, which is the one that has all the case statements for the add method. So let me actually try to dump this one. So it's just poking around a little bit here, which is kind of good fun, in my opinion. So here we go. This one looks more interesting. This is actually the one that we wanted to see. This is part of the call site table for the add method that actually has learned here that if the get type of both sides returns system system.int32, not system.int32, system.datetime, and system.timespan. You can't really read it in here, but load token is actually something, this is actually malprinted. It's malprinted. I should file a bug on that. This actually is really, this should be saying system.datetime, and this should be saying system.timespan over here, because it's basically comparing those guys. This is really kind of strange. We'll investigate that. But so what's going on here is it actually decided that in the case you have an int, if in case you have a datetime and a timespan, the best way to resolve that is by using the op_addition. That's what the C# compiler told the dynamic language runtime. In case you see that combo, please call op_addition. Now, of course, this thing is not only talking to C#. In case you have, for example, an object that comes back from either Python or Ruby or something else, what would really be happening here is the DLR says, hey, Python, I saw some Python object. Can you please tell me how to do an addition between two Python objects? And that may actually, generate an expression tree that does a whole bunch of, Python stuff that would be stuffed in here. So that's really exactly how the dynamic language runtime does its magic. And you see at the end of the day, modulo some if checks to basically find out which case it's in, it will actually do all of that stuff here. The reason it's doing some additional things is because, those are value types. But so let's actually go back here and just, wrap up. So for the dynamic discussion. So the basic idea is very simple. When you call a dynamic method, or when you do a dynamic operation, which you can see in Visual Studio by just hovering over the darn thing, the compiler generates a call site, which is this container that starts learning at runtime on how things have to be done. And every time it finds a case it doesn't know about, it's asking its buddy, in this particular case the C# compiler, please help me out here. Like, I now have two runtime types that I want to add together. Please figure out for me how to do that, and I will paste in that code in an efficient call site. So that's the idea of dynamic. So, and we can actually stop this one over here. So let's go back to this thing. As I said before, there's no way we can actually cover all of this stuff. Is there one more pick that somebody has? Something that looks fascinating. In fact, we've had the most complex ones in some sense. So, good picks. No PIA. Oh, no PIA. Okay, how many of you don't know the no PIA feature? Okay, not that many. Okay, so no PIA is this feature that allows you to avoid deploying primary interop assemblies when you're referring to, for example, the Microsoft Office automation APIs. No PIA essentially burns in the pieces of the primary interop assembly that you're using. It's burning them into your assembly. Let's try to do a very simple example of that over here. So if I go over here and I do right-click Add Reference and I go to the COM tab, I can actually import Microsoft.Office. Well, I should be able to import some Microsoft Office thing here. I think it's without the dot in between. I think I just imported something else here. Let's see, where's Microsoft Office in this list? I don't know whether I have everything installed here. Maybe it's Office. Is it Office? No, it's not Office. Have they removed this kind of stuff? Let's see whether it doesn't show up in here now. All of a sudden does it? Blah, blah, blah. Just a second here. Maybe I should sort it. Maybe I should sort it. Could be the case. Yeah, it wouldn't be in here. So it should be in the COM tab, as it always used to be. So let's just make... Oh, there's actually a search on the top. That's kind of useful. Thanks for the people who put it in there. Word. Word object library, that's good enough. That should be one of those guys that I can use here, I think. Let's see. That's not... Oh, yeah, okay, Microsoft Interop Word. Okay, good. I got Microsoft Interop Word for some reason. Okay, good. Microsoft Interop Word. This looks good. Let's see what's in there. Microsoft, whoops, .office, .word. No Word in here. That's kind of... Oh, interop, .word, .document. Okay, so here I have a document. And I want to do some interop with that. I'm not going to write complete interop code here, but here I could say, please, Word, create me a document, type, lorem ipsum in it, then save it to disk, that kind of thing. So you can basically just automate the whole thing. Let me just start by doing this. Now, this is actually already an interesting feature. I don't know how many of you have seen what I'm doing here. I did something weird here. Did somebody notice? It's an interface. How can I call new on an interface? Well, if you use COM, you can do a lot of things. So what's going on here is the compiler sees that this is actually a COM interface. It will translate the new call into a Marshall class helper call that actually passes in the GUID. Okay? So it will actually do a COM activation of that object. So this is the first thing that's kind of interesting about this, but this is not about no PIA. Actually, by no means this has to do with no PIA. Well, actually, a little bit, but let's just go here and show you that this is really the case by opening the console application here. And in program, where I do my new PIA thing, you see that that's really what's going on. It's doing marshall.getType from CLSID, passing in the GUID that's on the thing. So you can actually just do new on a COM interface, and the C# compiler knows how to emit code for that. And then it does activate a create instance to actually create that object. So that's kind of interesting. Now, what else do we want to do with this is, well, let's get rid of this because this generates a lot of code. But what I want to do here is I want to do something like doc.activeWindow. I don't know what I want to do here, but like activeWindow.activate or something, And likely this takes in a whole bunch of parameters. Oh no, I'm lucky here. But so I've just touched the active window thing. And if you would look at the Office interop assembly, it's really big. It's like a few megabytes of like all sorts of stuff. You don't want to really deploy that thing all the time. So what NoPIA does is it actually embeds all the things that you're using inside your assembly. So it's this flag called embed interop type set to true that triggers that behavior. Let me actually start by doing false. If I do false for this thing, and I do ILDASM, and I take a look at that file, what you're going to see in the manifest is that there is a static reference to Microsoft Office interop.word, which contains, of course, all of that stuff. But I've just touched like 2 darn members of something that's really huge, like the word automation model is really huge. So people complained about like, we need to deploy all of that stuff. We don't quite like to do that. And sure, lo and behold, everything sort of works. In fact, one thing you see is that the compiler generated different code for my new interface call. It actually found the co-class that corresponds to the interface inside the assembly and just used it up straight away. Now, when I actually do enable the embedding of interop assemblies and I recompile this whole thing, and now I go to ILDASM and open this file, what you will see is that, well, in the manifest, it only refers to mscorelib. That's good. It no longer requires this other assembly to be deployed, and it has copied all of the things that I somehow have touched directly or indirectly from the word automation model, which is really small compared to all of the stuff I was using before. For example, I'm using document. Okay, for some reason I'm using document, which implements a certain interface called _document, which is sitting over here. Document contains the active window getter, but the active window getter is sitting in a vtable 50 slots away from the start. So the CLR also emits over here like a little gap in the vtable so that when you actually run this thing without having the real Office interop assembly, it can actually jump to the right place. So that's what you're seeing here, and it actually just contains, everything that I was using indirectly somehow, through that little simple thing. Like, for example, over here, the activate method apparently is also in a vtable gap of some distance. So essentially see that, by enabling this NoPIA stuff, you actually don't have to deploy the whole Office interop assembly. And then you also see that the constructor call over here is actually simply doing the Marshall stuff, as I mentioned before. So that's actually what there is to be said about the NoPIA feature, which was introduced in .NET 4.0 in conjunction to the dynamic feature. Like, one of the big cases for the dynamic feature was really enabling Office interop scenarios. And so to do Office interop, PIAs were sort of like, one of those, things that were sticking out to look at. Okay, so I have a couple of minutes left. Let me actually pick one little thing myself here, okay? And this is just having some fun with the switch statement. May wonder, like, the switch statement, what's so funny about that one? There's a lot of funny things that we can actually tell about the switch statement. But like one particular case that's interesting is this one. Have you ever wondered, like, what happens if you switch on a string, right? So if I have string, string args over here, and I want to switch on the first command line argument, parameter or something, which is switching on a string. Well, there are certain languages that can't switch on strings, right? But somehow C# can. So when I say case bar, do something, like, and the something I will do is just break, and let's do case foo, I will also just break over there. So I can start writing those case statements. Like, how does this thing really execute? Okay. Well, let's actually figure out. I'm just going to compile this without the optimizations because it may actually be super smart and say, like, you're not doing anything in there anyway, so why should I bother? But let's take a look at how this thing actually compiled. This thing just compiled as doing something like, load the local variable over here, load the string bar, and do an equality check. If those two things are equal, jump to the next, to the label that executes that particular piece of code. Else, do another equality check. This starts to look like if, else if, else if, else if, else if, else if. Like, shouldn't the switch be more, optimized? And the answer is absolutely. Like, a switch can be much more optimized if there is enough reason to do so. So, let me actually go in here and, add a few more cases, right? Let me add, some bar 1, some foo 1, some bar 2, and some foo 2. Let's see what's going on now. So let me recompile first, otherwise the whole demonstration is kind of moot. But so let's take a look at what's going on. I have 6 cases now. Still nothing's going on. Like, it's still if, else if, else if, else if, else if, else if. Okay, mysterious. So what about adding a 7th one? So if I add a 7th one over here, and let's call that thing quux, right? So here we go, here's the 7th one. Now let's take a look over here. There's something called private implementation details that was generated by the compiler. What's contained in the private implementation details? There's a dictionary of string to int32 there. It's a mapping table that contains all of your case labels and maps them onto an int. Because now what we can do is we can say, let's take a look in the dictionary to find a number that corresponds to each of the strings in my case labels, and then I can use a switch that's built into the CLR to do an efficient switch based on a number, which is basically just computing an offset and doing a jump in terms of the instruction pointer. So if I take a look over here, this is really what's going on. It's actually saying, with a volatile read, in case there are no private implementation details yet, I will start creating them. I'll create basically a dictionary here that does an add of, the first case, the second case, and so forth. So it's basically building up this gigantic table. In the other case, it's going to actually bypass that initialization of that code, and it's just going to do something like try get value. It's going to say, let's take a look in the dictionary and find for that string what's the corresponding number. And now once we have those numbers, we can actually build an efficient switch table that says, if it's case 0, which corresponds to bar, jump over there. In case it's case 1, which corresponds to quux, jump over there, and so forth. So you see, like, this is one of those, little optimizations that you sort of may wonder, like, how does C# do it? Well, it turns out that depending on the number of things, it picks a different strategy. And so if you play a bit more with, switch statements, you will actually find that they are really beautiful treasures of little optimizations in some cases. So with that, in fact, I should back up here. We looked at quite a few of those, features. There's always more to talk about, and it happens like a little shameless plug that I also wrote a book on C#, which contains a lot of those tidbits. But I have done a couple of videos on this from previous events, so you can actually find videos which will have a different selection of features. So if you all paste them together, you actually end up with the full a la carte menu. My plan is to actually keep adding those things, and so if you find a case and you say like, oh, I would like to know how this particular thing works, you may actually see it show up in future editions of this talk. So with that, I think I'm done for Tech Days 2013 in Belgium. If you have more questions, I will be around till some shuttle bus arrives for Tech Days Netherlands. So I will be around for, I believe, 1 more hour or something. So if there's more questions, please come and find me. Otherwise, thanks for coming and thanks for your attention.